Today we will be looking at the kinematics of circular motion. We will discuss the angular displacement. We will look at the angular velocity, the velocity, acceleration in a circle, and the forces that are involved in a circle. Well, there are many uniform circular motions: the spinning of a wheel, the circular orbit of the Earth, the satellite that's moving around the Earth, the London Eye, and a car that is moving in a circular motion. Many motions are related to circular motions. We will summarize the relationship between the degrees and radians to understand the angular displacement, angular velocity, and connect angular velocity to the period and frequency of rotation. And we will connect angular velocity to linear speed. Okay, when we look at a complete circle, let's say this is our starting point, so that means no displacement. When we move into 90 degrees, we have a displacement of pi over 2, and we express this in radians, 90 degrees. When we have an angular displacement of 180 degrees, we have pi radians. Okay, and when we make a complete circle, we have 360 degrees, which is 2 pi. So angles can be measured both in degrees and radians, and the angle is in radians is defined as the arc length divided by the radius. For a whole circle, we get then the arc length is 360 degrees, and the circumference then is 2 pi r. 360 degrees is 2 pi radians, and we have other common values like 45 degrees is 1 over 4 radians, 90 degrees half radian, 180 degrees pi radians. Okay, so for one complete rotation we have 2 pi radians. Remember, we use rad. So how many degrees are in 1 radian? You can calculate, not too difficult. Angular displacement. The angular velocity for a circular motion is similar to the linear motion, which is the displacement over time. The time remains unchanged, but the linear distance d is replaced by the angular displacement, measured in radians. So angular displacement is the number of radians moved. Okay, for watch, how can we calculate the angular displacement in radians on the tip of 1 second? Now let's say we have a clock, and this gives the hour, that one gives the minutes, and this is my second. Now what I want to know is, what is the angular displacement of the big tip, whatever you call it, 1 second, 1 minute, and 1 hour. Now, if we have 1 second, 1 complete round is 1 minute. So for 1 second, it is 1 divided by 360 times 2 pi. If we have 1 minute, we have 1 complete rotation, so that is 2 pi. If we have 1 hour, then the tip is going to make circles 60 times, so we get 60 times 2 pi for 1 hour. How would we calculate the rotation of a London Eye if it takes 30 minutes? What is the angular displacement for 1 second? Well, that is 1 second over 30 times 60 times 2, well, we take the degrees, times 2 pi. Do I say that good? divide by 360. Okay, well, you know how to do this. Okay, all right. Angular definition. Consider an object moving along an arc circle from A to P at a constant speed. So for the time t, the rate of change of the angular displacement with the time is then we have the angle in radians. So we can write our definition for the angular speed is the angular displacement in the amount of time. So where the angle is the angle turned through in radians yields the units for rad per second. This is all comparable with the linear speed as we discussed before. Now, how do we relate the angular velocity with the period and the frequency? Now, for the time period, that means we have a complete rotation for 2 pi radians. So we can substitute that in our angular velocity. So we get for the angular velocity is 2 pi over time period. And then we can rearrange the time period in 2 pi over the angular velocity. And we know that t is 1 over f, or f is 1 over t. So we can also rewrite the equation as frequency, the angular velocity divided by 2 pi. How do we relate with the linear speed that is traveled in the arc length? Now we know that the linear speed is the arc length divided by t. So that means we have the involvement of the displacement of the circumference. Okay, so if we substitute, we get v is r times angular speed. Now remember the angular velocity, let's say that one is constant. That means no matter where we have the position, the angular velocity is always the same. However, the velocity is increasing when r is increasing. So here we have same angular velocity, but it changes and increases with the r. Okay, let's see this question. A cyclist travels at 12 meters per second on a bike with wheels which have a radius of about 40 centimeters. Calculate the frequency of rotation for the wheels, the angular velocity for the wheels, and the angle the wheel turns in 0.1 seconds in radians and in degrees. Now, the frequency of the rotation is pretty simple. Circumference of the wheel is 2 pi r, so 2 pi times 0.4 meter, we have 2.5 meters. The time taken, or the time period, s is d over t. We can rearrange it, and then we find for the t 0.21 seconds. And in order to find the angular, the frequency is 1 over t is 4.8 hertz. The angular velocity for the wheels, t, is 2 pi over w. We can rearrange, and then we find for the angular velocity 30 rads per second. Okay. Now the angle the wheel has turned through 0.1 seconds in radians. Angle is wt. Angle is 3 rad times 3 over 2 pi times 360, and then we get 172 degrees. Okay, we start with our next slideshow, and that is how is the centripetal acceleration and the centripetal force related to the motion in circles. We see here some different actions wherein we have an inertia and roller coaster in a circular motion. We have weight, we have centripetal force, someone who's trying to throw a ball connected to a string. We have centrifugal force, centripetal force. Be careful, centrifugal force is different than centripetal force, but mainly we use centripetal force. Okay, some learning objectives. Consider the speed and velocity around a circle. To consider the acceleration as a change in velocity, and we define an equation for the centripetal acceleration and define an equation for the centripetal force. Okay, centripetal acceleration. There is a derivation of this, but we can go through it, but I go pretty fast through it. You don't need to derive it, but you need to know the formulas. Yeah. Remember, when an object is moving in a circle with a constant speed, the velocity is changing constantly. Because there is a constant change of the velocity, that means the object is constantly accelerating. Yeah? So, if the object is accelerating, then an unbalanced force must exist. Let's look at this example. We have an object moving in a circular motion with a speed which moves from point A to B in delta t seconds. We can use speed is distance over time, so the distance moved along the arc AB, delta S is v times delta t, and we can use a vector diagram to show the change in velocity. The triangles ABC and the vector diagram are similar, so if delta angle is small, then delta V over delta V is delta S over R, and we can substitute this, and then at the end we can get actually the change in velocity, which is the acceleration over time, is delta V over delta T is V squared over R. So the acceleration taking place in a circular motion is V squared over the radius. We can substitute for the angular velocity. A is V squared over R, and we saw that V is R times W. We substitute for V into the above, and then we get for the acceleration is A equals R times angular velocity squared. Now, if we know the acceleration, we can also calculate the force involved in a circular motion. We know that F is m times A, making use of the circular motion, so we get F is mv squared over R, or the force is mrw squared. So any object moving in a circle is acted upon a single resultant force towards the center of the circle. And this is what we call the centripetal force. Now, why are these bodies kept in a circular motion? Now, let's look at a satellite that is moving around a planet. Now, it is the gravity that keeps the satellite in orbit. Okay, so the Earth and the Earth around the Sun is a classic example. When the Earth is in orbit, around the Sun, it's a classic example of a centripetal force. Let's see if we can calculate. The wheel of a London Eye has a diameter of 130 meters and takes 30 minutes for one revolution. What would be the speed of the capsule, the centripetal force? What would be the centripetal force on a person with a mass of 650 kilograms? The speed, we can use V is R times W. We know for full rotation 2 pi rad in 30 minutes, so we can calculate the speed, which is 0.323 meters per second. Therefore, we know the radius, so we can calculate the acceleration, and the acceleration is using A is V square over R, so that is 7.92 times 10 to the negative 4 meter per square second. Now, because we know the mass of an object, we can calculate the centripetal force, that is 65 times 6.92 times the acceleration equals is 0.051. Yeah, I just had to double check. Okay, another question. Let's see if you can calculate this one. Just some practice. Object of mass 0.15 moves around a circular path which has a radius 0.42. Once every 5 seconds at a steady state, calculate the speed and acceleration of the objects. The centripetal force acting on the objects. Pause the video, try to calculate. The answer is 0.8528 meters per second. The acceleration is 0.663 meters per square second, and the force acting is 0.1 Newton. Our last slideshow about centripetal motion. I go quickly through this, so I hope you can follow this. Yeah, it's just a revision, okay? So some examples we will work out. And you can see there are many ways, different forces that are acting on a body when there is a circular motion. So our learning objectives are to show the centripetal force provided by the real world forces. So to keep a motion in circle, it is actually the tension or the gravity or the friction that keeps the object in that motion. Okay, we can consider some different examples. Over the top or a humpback bridge, around flat curves or around banked curves. Now, what we see is that an object in a circle has a constantly changing acceleration. That means it is experiencing an acceleration and hence a force towards the center of rotation. Now, we call this the centripetal force, the force required to keep the object moving in a circle. And this can be provided by the tension in the spring, friction, or the force of gravity. Some recap formulas: A V square over R, A R W square, F is mv square divided by R, and F is mr W square. Oh dear, something has happened here. Okay, let's consider over the top. What do we have? We have a support force and we have the gravitational force. And it is a car that is moving with the speed, moving over the top of a hill. Now, when we look at the top of the hill, the support force, S, or normal force, is in the opposite direction to the weight. It is the resultant between these two which keeps the car moving in a circle. So in this case, mg minus S, the support force, is mv squared over R, If the speed of the car increases, there will be eventually a speed v0 where actually the car is leaving the ground. That means there's no support force anymore. That means that the gravitational force of the car equals to mv0 squared divided by r. Yeah? And you might have experienced it. I used to do it sometimes when I was with my girls and I saw a bridge and I was making a big bump. I speeded up a little bit and I felt that force actually, that lifting up. What is happening here when we go around about? We make that circle. Now, what is the force that keeps us moving in a circle? It needs to be a force going inside. Which force is that, you think? That is the friction of the tires. Okay? So it is the friction that keeps the car around about, and it is providing the centripetal force. So in this case, the centripetal force required to keep the car moving in a circle is provided by the friction between the road surface and the tires. So we may say that the friction of the force equals to mv squared over r. We are not going to use this because in the A level we don't use the coefficient of friction, but just to give you an idea what is the coefficient of friction and how can we calculate the friction, it depends on the normal force acting on the car, and the higher the normal force is acting on the car, that is the contact force between the car and the surface, the higher the friction. It also depends on the surface area, and the surface area is like a constant. We have a static and a kinetic friction coefficient, and they depend on the type of surface. This one, that's an interesting one. And here you have to look closely what is going to happen. I think we made already some questions that are related with this movement and the forces that are acting on it. Okay. So for high speed travel, racetracks, etc., they have bank corner. In this way, a component of the car's weight is helping friction to keep the car moving in a circle. This is nothing more than use common sense, and use common sense with all the forces that are working on the car. Okay. If there would be no banking, the centripetal force is only provided by the friction. If we have bank corners, it can allow us to have greater speed before friction is overcome due to the gravitational force. We can rewrite the different forces and equal them to the centripetal force. We don't discuss this rearrangement. You may look at it, it's not so important, but just understand when you have a question about this, analyze the forces good, what are the directions of the forces, and how do you get to that there is a balance between the friction and the gravitational force that keeps the car moving in a circle. Haven't been working out this, but you could maybe work it out using the formulas, but in the A level we discuss it a little bit in a different way. You could look at this as well. Okay. Just work out the forces, and then you can find the different forces acting in the car. Okay. Now let's look a little bit at centripetal forces and a fair ground. We have applying all the things that we are learning in the circular motions to consider three different particular cases of motions: the Big Dipper, the long swing, and the centrifugal wall of death. The Big Dipper, we call it. And it's interesting to know what is happening here. At the bottom of the Big Dipper, you are pushed into your seat and you feel heavier. Yeah, what is happening here is that you have the force of gravitation and you have the normal force. So, when we are at the bottom and we are going to resolve the vertical forces, then we could rewrite the support force minus mg is mv squared divided by r. So actually the support force is mg plus mv squared divided by r. So you feel that extra weight when you have the feeling that you're feeling heavy is given by that centripetal force. Obviously, when you are at the top, you would feel lighter, okay? Because now you have mg this way and you have the support force this way, okay? The long swing. Consider a person of mass m on a very long swing, and we're going from the top to the bottom. We have an initial position. Now, as the swing is released, we can consider the conservation of energy. Now, the energy is coming from the potential force, which is turned into a kinetic energy. So we can calculate the velocity at the bottom. As we know already the velocity, we can calculate the force by the circular motion. So on the bottom we have S minus mg as just before. Remember the other example I asked you about, and then we get the support force is mg plus mv squared plus r. And again, when you are making that swing, at the bottom you feel that support force is bigger, and when you are more to the top you feel much lighter. Okay. We can rewrite this in another way, yeah, but not that so important, but just understand that you feel heavier when you are at the bottom, yeah. The wall of death. Well, here are some other forces working. Okay. We're not going to discuss the wall of death, but that is the force acting on the side. We have a velocity and we have the rotation of the weight, yeah, and it's like you have to get enough speed so that actually you are in balance with the wall of death. I think that's it. There are many examples that we discussed already. Look especially at those questions wherein the forces are involved when we have banking. Okay, yeah, that's it for circular motion.